Sure, yeah. Everybody, I'm Lucas. Some people know me better by cronokirby, so that's also me. And today we're going to be talking about threshold ECDSA. So 90% of this talk is going to be about how to multiply two numbers. And otherwise, we're going to talk a little bit about beaver triples and other cool stuff. So as a little overview of the talk, we're going to be talking about what ECDSA is. It's a signature scheme. What it means to thresholdize it, why it's harder than other schemes at least, what some existing approaches look like, and then also some stuff I've been working on called Cait-Sith. So ECDSA, everybody's favorite signature algorithm. First of all, I'm going to explain how elliptic curve cryptography works to you in 10 seconds. So you have scalars on the left, that's the F. You have group on the right, which is points. You can add and multiply and divide scalars. You can add group elements, addition, right? And you have this special map, which sends a field element, a scalar, into a point. And if you add two, oops. Time is relative. And so if you add two scalars together, this map preserves that. So x times g plus y times g is x plus y times g. That's all you need to know. So this is ECDSA, the signature algorithm. In red, I've highlighted the stuff that has to be kept secret. So your secret key is x, and k is a one-time secret you generate when you sign. So you generate this key at random, you invert it, you multiply that by g, you get a public point, you hash that. It's not really hashing, but whatever. And then you have this final equation where you do k times m, which is your message that you're signing, plus r times the secret x. And that gives you your final signature, big K and little s. And this is just sort of your standard signing thing where one person signs with their secret key. But what we're interested in is the threshold signature setting where you have one secret which is split into multiple small shares. So here I've sort of illustrated three people coming together to sign a message using their shared key. The usual way sharing works, up at the top left, is that you just have sort of additive shares. The threshold things we talked about in the previous talk sort of apply here because you have some other representation with polynomials or whatever, but you convert these into additive shares. So at the end of the day, when you need to sign, you have x equals x1 plus x2 plus whatever, however many parties there are. And the idea is that for k, this is also the representation you have. So if we look at the signature scheme, we have the following operations which use secret red elements. So we need to generate a random value that's shared in this way. We need to multiply it by a constant value. We need to invert it. And we need to multiply two red things together. So the first one is easy. If you want to generate a secret like this, just have each person generate their share on their own, and then you automatically have this sharing. So that's easy. Multiplying by constant, also easy. Each person just multiplies their share locally, and you're done. No interaction needed. The hard part is inverting and multiplying. In fact, the hard part is just multiplying because you can get around inversion like this. So here in brackets, I'm introducing some notation. This just means a secret shared value. So this value is split among everybody and nobody knows it. So if you have some secret shared value delta, if you divide by a public value delta times k, well, what ends up happening is you get a secret sharing of 1 over k. So if you have a way to multiply two values that are secret shared, you can use that to divide. So all we need to do is figure out how to multiply two secret shared values. And that's what the next 16 minutes of this talk are going to be about. So multiplying numbers, how hard can it be, right? Well, it's actually pretty hard. So the basic issue is that when you sort of multiply two secret shared values, the multiplication distributes and you get something like this. So you have x1 times k1, x1 times k2, etc. So in blue, you have the same value on each side. So it's x1 and k1 or x2 and k2, so that you can do locally because it's just owned by one person. The hard part are these shared things where you need some kind of interaction because one person has x1, the other person has k2. So they need to interact somehow to get the result. So the usual approach, and if you generalize this to sort of n parties, you get like this sum. So the usual approach is like you use what's called multiplicative to additive conversion. So you have two values, a and b. One person has a, the other person has b. and they want to get two new values, alpha and beta, which sum to the original product. So you had A, B, they give you A, B when you multiply them. You want to somehow, through some protocol, get alpha and beta, which sum to A times B. And there's sort of two approaches to this that are sort of popular in sort of mainstream protocols. The first one is based on homomorphic encryption. So what this is just an encryption scheme, public key, so I can encrypt to somebody's public key without any secret, and only they can decrypt it. And the idea is that this operation has this special operation called like box plus or whatever, and the idea is that I can do this special operation on the ciphertexts, and what ends up happening inside is that the plain text values get added. So if I have a ciphertext for number A and a ciphertext for number B, and I do this operation, the end result is going to be a ciphertext which encrypts A plus B. And as a consequence of this, if I want to sort of add a ciphertext to itself n times, I can do that, and the end result is sort of multiplying whatever is inside the ciphertext. So you have this sort of operation that sort of slides around the encryption window. That's one way of looking at it. And the reason this is useful is that, well, it sort of gives you an MTA protocol kind of out of the box. So remember, we have one person has A on the left, the other person has B on the right, and they want to get shares alpha and beta, which sum to A times B. So a simple way of doing this is one person sends the encryption of A, and they encrypt it to a public key that they control, so only they can decrypt it. The other person, they have this encryption of A, they can multiply it by B, which gives them A times B, but encrypted, and then they can add some value minus beta. And they know beta that they've generated at random, and then the idea is that when the person on the left decrypts that value, they're going to get A times B minus beta. And the other person knows beta, so now they have these two shares. And that's sort of all there is to it. The hard part is making this sort of secure if people are allowed to cheat and not follow the protocol. Another way of doing it is oblivious transfer, which I didn't put any slides into because I didn't think I would have time to talk about it. But it's basically not like this at all. That's the best way of explaining it. So it's simpler, but it's also more complicated. But here are the important things to know if you're like evaluating these things. So homomorphic encryption on the left, I put slow with a question mark because the way people do it in practice is using something called Meier, and Meier is like RSA, but worse. And it's kind of slow, and it's kind of hard to implement in constant time. But you can also, in theory, do this with lattices. People haven't done that for ECDSA for some reason. They've used sort of this kind of lattice technique for multi-party computation in general. So there's some Spuds papers that use this, if you know what that is. And another thing that's sort of tricky with the Meier approach specifically is that if you want to make things maliciously secure, where people are allowed to cheat, you basically have to add zero-knowledge proofs for everything. So at some point in these papers, there's like zero-knowledge proof that like an RSA modulus is generated correctly. It's like a zero-knowledge proof that like an encryption of something corresponds to an Elgamal ciphertext. It's like there's like these gigantic proofs that take like hundreds of pages, and there's like 90, 100,000 page appendices with all these proofs, whatever. Oblivious transfer, sort of a bit easier to make maliciously secure. There's some downsides though, which is that you have to send a lot of data. So the sort of rule of thumb is that with the homomorphic encryption approach, you sort of send one piece of data for doing this sort of multiplicative to additive conversion. And this piece of data is like, kilobyte. So a scalar is like, 256 bits, and you send maybe like 1,000 bits. So it's not like too bad. With oblivious transfer, you need to send like a packet of data for every bit in the scalar. So if you have 256 bits, that becomes like, 256 kilobytes. So you have to do megabytes of communication in the end. And so that makes it so that if you have like a very large scale deployment where networks aren't very fast, this is probably worse. It's also like a lot more code in practice to implement. It's not more complicated code, I'd say, but there's just sort of a lot of layering because oblivious transfer is a very like little protocol, and you have to somehow layer this into this complicated functionality. So it takes a lot of effort to do that. I have to point that way. So this is not my problem. So basically, I've worked on sort of a new, quote unquote, threshold ECDSA protocol, which sort of avoids this issue entirely. So sort of like, if homomorphic encryption is Catholicism and oblivious transfer is Protestantism, I'm an atheist in this debate, right? So basically, Instead, I say multiplication is not my problem. My protocol is going to assume you've already multiplied. That's your job. That's not my job. So we introduce the triple, of which there are too many. So the way multiplication triple works is that you have random values A and B, which are secret shared. And then the fun part is you have C, which is the multiplication of the two, which is also secret shared. So in advance, you've prepared these triples. And you've sort of already done this complicated multiplication protocol in advance on values which have no relation to any of the secrets or whatever. So if these get compromised, no biggie, as long as you don't use them. And the reason why these are useful is sort of by having already computing a multiplication on random values, you can use that for stuff you care about somehow. So it's probably the most complicated slide. So on the left, you have k and x. Remember from way back when, these are the things we want to multiply. And on the right, we have a, b, and a times b. All of these are secret shared. And these are sort of two random values which we've already multiplied. The issue is that these are random values we don't care about. We want to multiply the things on the left. So can we somehow reuse this work? Well, we can. So the way the protocol works is that first, each person locally computes k plus a and x plus b. And you can do that in a secret shared way because these shares are sort of additive. So I can add them locally, and then they publicly reveal these values. And so then these become public. Each person reveals their share. And the reason this is fine is that a is a random value. So if I reveal k plus a, that doesn't reveal any information about k. As long as a is used only once. Very important. Same for x and x plus b. And then you use this sort of formula at the bottom. And this formula just works, basically. So if you do the math, everything cancels out except k times x. So at the end, if you just do this computation locally, you get a share of k times x. Because, and crucially, use the fact that a times b was secret shared before, and this sort of multiplication allows you to sort of transfer, in some sense, the multiplication from random values to values you care about. And this is sort of the idea behind Cait-Sith, which, I mean, if you can guess what it's actually an acronym. And if you can guess what the acronym is for, I mean, good job. And so this is a protocol I've been developing and implementing, which sort of takes this idea to the limit. So like, what if you're extremely lazy and you just want to use triples? What does that get you? So diagrammatically, this is what the protocol ends up looking like. So you have key generation, which you can do as Philip talked about, or you can just do it in like more boring ways, which have less desirable properties. But anyways, you generate your keys, and then you have a pre-signature phase, which you can do before you know the message, which does basically most of the work of a signature, and that requires some triples, 2 of them. And then once you know the message, you can use a pre-signature to finish the signature. And then with triples, you need to do a setup thing, which is sort of like a keygen for like having some correlations to be able to generate triples efficiently. And then for each time you need to sign a message, you need to generate two triples in advance. But these can be generated far in advance, and you can generate like 100 triples at once or whatever. So you don't really care about the cost of this. Also, I haven't implemented triple generation yet, but I have implemented everything else. So I can talk about benchmarks that are very blurry, because I was too lazy to run the benchmarking again, so I just used like a tweet that I made like a few months ago. But I mean, my computer may have gone slower since, but the benchmark shouldn't have changed too much. So anyhow, you have pre-signing, well, first you have keygen. So generating keys with 3 parties, and this is just computation, no like communication stuff. Takes 3 milliseconds. Pre-signatures takes 8, and then signing takes less than 1. So if you count pre-signing and signing as just like one thing, it's like 10 milliseconds. And like from Philip's talk, you had like 70 milliseconds for keygen, so this is a lot better. Apples to oranges, but And also, I'd expect if I implemented the triple stuff, which I've specified but not implemented, it would be like 100 milliseconds, 200 milliseconds. The reason that's not like the best benchmark is that triple generation is very communication intensive. So if you don't model the fact that the network is potentially slow, it's not like really an accurate benchmark because you're doing a lot of communication. So if you're trading off more communication for less computation, that's going to give you great benchmarks, but maybe not real-world performance. Also, everything in the sort of protocol has been specified to like a certain degree of detail. So everything's already written down. I just haven't implemented everything yet. Been busy with lots of other stuff. But yeah, you can also go read it. It's been open source since like I started working on it. There are sort of docs for like, maybe people will be interested in the specifications, and also all the code sort of open source too. So you can go check that out. And otherwise, I guess I finished a bit early. I thought there was going to be a lot of stuff to talk about, but yeah. Thanks.